Okay, in these two scenarios, which one is a positive moment? So talk to the person next to you. Which one is a positive moment? So on number one, does it look like for the x-axis is twisting towards you or twisting towards the board? It's twisting towards you. On the right one, is it twisting towards you or towards the board? Towards the board. So let's put our fingers. If the first one is twisting towards you, your thumb is pointing in the positive x direction, right? And on this one, my curve, if it's twisting into the board, my thumb is pointing in the negative x direction. So which is positive? This one is a positive moment, and this one is a negative moment. Good? Okay. I want to say, just going back, Evan, you recorded that last homework, right? Homework 3?
Yeah.
Right? You guys are doing great on your homeworks. I mean, there's very little marks that I have to write in there. And if I wrote any marks on your homework, it's all written on the first page. It says see comments or see notes or something. But you're doing really well. Okay, so everybody has this, right? Draw these pictures. Make sure that you're comfortable drawing this. Here's another situation. You can see the difference in the drawings, right? The space here means that the x-axis is in front of that curve, right? Here, the space is here because the x-axis is in front of that. What kind of spin is this? About what axis? The z-axis. There's no space here. That means that this curve, this circle, is spinning on this plane, on the xy plane, which means it must be spinning about the z. Is it positive or negative? Positive. It's positive. So this was positive about the x-axis, this was spinning in the negative x direction, and this is spinning in the positive z. Please draw these down, because I want you to make sure that you are drawing things correctly. You have to remember to draw it in 3D, which means you have to leave a space. So this is practice on drawing things correctly. Everybody good on this? Let's move on to the next.
For the first one, if positive x was defined going to the left, and you still had that same rotation.
Okay, so let's try it. If x positive is going to the left, and I have the same drawing, like this, is this what you mean?
Yeah.
Okay, so let's look. So my fingers are going this way, right? My spin is going this way, but the positive x is going that way. So which is the correct notation? Well, you know what? We're never going to have this. We never put x to the positive. But if we did, when I do my spin, does everybody agree that it's spinning towards us? If it's spinning towards us, my thumb is pointing that way, it would be a negative spin. So it would be going in the negative direction because my thumb is not pointing in the positive x. Okay, but that's a good question. You always want to make sure that the positive x direction is denoted with my positive thumb. Or rather, a positive spin is when my thumb is going in the same direction as the positive axis. Yeah, Janae?
So why is there no space on the bottom one, the one that has positive Z?
Because it's not three-dimensional. These two, because there's a space here, it's spinning out at us and it's spinning in. This whole thing is rotating,
Okay.
right? So it's rotating like this on the plane of this board.
So you'll see that at the pivot position, where it pivots. That.
Good question. It could be pivoting anywhere, and they'll tell you, let's just say yes. Yes. And then we'll look at examples, because we're not running into this yet.
Okay.
So yes, for now. Okay, let's move on to the next thing. I see people make mistakes, and it's not because you're making a mistake because you don't know it. You're making a mistake just because you aren't thinking or you're a little sloppy. So I want to point out that mistakes are made sometimes, so we're going to do this. So if you have a force that's going from A to B, I want you to calculate, what does E stand for? Univector. Kind of weird notation for univector, but we're going to take it. Find what the unit vector is, and then I want you to find out what the R vector is. Write it down. Okay, Santiago, how do I calculate the unit vector?
It will be the force times the x and y components divided by the magnitude.
Okay, and if we did do forces, well then you know how we would do it in a three-step process, right? But I'm only looking for the unit vector part. So the unit vector part is only the part that shows the direction. It doesn't have the value of the force in it. So tell me what to write.
It will be 3 over 25 and 4 over 25.
Okay, and it's actually not over 25 because it's going to, right, it's going to be a 5. So could I write it like this? This way I'm only writing 5. This way I'm only writing 5 once. Just saves me a little bit of time. And what does that turn out to be? Somebody give me the number. Jack, give the number.
6.6i plus 0.8k.
Okay, and I'm going to put 4 decimal places. Does a unit vector have any units? No, no units at all. Okay, Nick, what's my R vector going from A to B?
It's 3i plus 4j.
4j. Does it have any units?
Oh yes, it will actually.
So let's write.
Like the distance.
You guys like metric? I'm getting the feeling.
Yeah.
What is it?
Yeah, we need to.
You guys only like metric because that's what the physics department you came from. You came from the metric world. But before that, you came from the English system world.
Yeah, but we hated it.
And like I said, in engineering, you do both. Okay, so what is the relationship then of the unit vector to R? Because there's an R just in there. The unit vector of, oh, that's a really big circle in the E. Unit vector AB is equal to what, Nick?
Unit vector AB is just
How do I relate these two guys? The unit vector and the R.
unit vector is R just one unit long.
Right, so R, AB over
Oh, the magnitude.
of the magnitude. How's this? Is it okay if I do this? Magnitude of RAB? Right, which is 5, right? So isn't this true? We said it was 3I plus 4J over 5. Comes out to be the same thing. So just remember, there are times you're looking for the unit vector, and there are times you're looking for the R vector. And you know the difference. It's just sometimes you write R by accident instead of the unit vector, and there are times you write the unit vector by accident instead of R. I just want to spend 5 minutes reminding you they're different. Make sure you check your stuff so you make sure that you're using the right one. Okay? And they're related. Which one has units?
R.
R. Okay, good. Okay, so now we're going back to, we did 2D right-hand rule, we did 2D vectorially, we did 3D vectorially, and now we get to do 3D right-hand rule. It's probably my favorite. And some of you are going to get stressed out about it because you're not going to be able to get it right away, but it's no big deal because you're going to get it as you go along, and you're going to get better and better at it by 3/4 through the semester. You're no longer going to want to do it vectorially ever again. You're going to want to do it 3D right-hand rule all the time. And you want to get better at it, and you want to be able to do 3D right-hand rule. Because if you're designing, I know I use a bike too many times maybe as an example, but if you're designing a bike and you know what kind of loading is going to be on the seat, you need to be able to look at it and say, oh, that kind of force creates that kind of moment on that frame because it's this force times this distance, and you're going to get the answer like that. You are not going to want to sit down and write out an R vector and write out the force vector and then do a cross product. You just don't want to do it. It's too mathy. You want to just be able to visualize it and say, okay, this force is going this way. Here's the bar I'm trying to find the moment about. I'm going to say R times the perpendicular distance, and I'm going to get a value like that. Okay? Okay. So we already solved this problem. We found the moment about point C due to this force vectorially. And let's just write down what the force was. So the force vector was AB 400I plus 500J minus 360K. Okay? So we already solved for the force vector. We already solved for the moment vectorially. Let me write that down. Evan, could you go get the tops? So go into my office, go into the back room, go all the way to statics, and you're going to see a box of tops. So the first thing you want to do in the right-hand rule is draw the forces. They're coming off point A. Oh, I'm sorry, there was something else I wanted to mention. Chelsea, the other day you asked me, when you do the R cross F vector, everybody should have got the sheets up here. Pull out this sheet. It says moment about a point on the top. Mom about a point. Chelsea, you asked, do you always have to do the force, like, let's see, for this example, what we did is we said the moment is equal to R cross F. F went from A to B, and the moment I needed to find about C, right? So my R vector went from where to where, Chelsea?
From C to A.
C to A. C to A. So it went from the point I'm finding the moment about, right, to the tail of the force. And Chelsea's question was, do I have to do it to the tail of the force? You do not. So what I did is I solved for a problem, solved the problem, and I solved for it having R, oh here, over here. So take a look at this. We have a force going from B to C, and I wanted to find the moment about point O. So I did, that was fast, thanks. I found R from the tail, the point I'm trying to find the moment about, to the tail of the force. But then I did it the other way to just check what Chelsea said. And here I still did the moment, the force, the R vector going from the point I'm finding the moment about, but instead I found it to the head of the force. And the answer comes out to be exactly the same.
You move it up a little.
Yes. Thank you. The answer comes out to be exactly the same. Because remember, when a force goes from A to B, it's not just a magnitude, it's a magnitude and a direction. Really, B could be considered its tail too. It's still pulling it in that direction. So that means that you could find R to any point along the force. But the beginning point of the R has to be what point? The point I'm finding the moment about, right? The beginning of my R vector has to be the point I'm finding my moment about. And the tail of the R could be whichever. But I always do it this way. I always find it to the tail of the force because I'm less likely to make mistakes. If I pick one way of doing something and I always do it that way, I have less chance of making mistakes. So I always do it from the tail of the force. So that's the way you're going to see me do it. But you can do it to any line because when you cross R and F, what do you get?
A vector.
You get a vector, and you get a vector that is perpendicular to both of those vectors. So whether if the R vector is here, and my force is here, or here, or here, they're all in the same vertical line, vertical plane, whether they're here, here, or here, they're all in the vertical plane, and the force, the moment you're going to get is going to be perpendicular to that plane. Okay, let's go back to this. So the first thing you want to do when you're doing a 3D right-hand roll is you take your force and we're going to draw it. They have it drawn in 3D. It's coming off point A. So I want to draw 400I. And here's my x-axis, right? So I'm going to do it a little bit lightly to begin with. I want to make sure that I'm drawing it parallel. That's not really that great. That's better. That's parallel to the x. This is parallel to the z. Oh, and from now on, you guys always ask me for stapler, and I got these. And a hole puncher. They're in here now, always. Okay, so the first one is 400. So in the x direction, I have 400 newtons. In the y direction, I have a positive 500 newtons. And in the z direction, there's a negative. So I'm drawing it in the negative direction of 360 newtons. Does everybody see that? So in the y direction, in the z direction, and in the x direction. Everybody's comfortable with this so far, right? Are you alive?
Yes. Yeah.
Is everybody comfortable with that? Okay.
Yes.
Now, what am I finding the moment about? And this is what Rachel had asked the other day. If I'm finding the moment about point C, and I'm calculating the x, y, and z moment about z, I'm actually calculating the moment about the axes going through C. So let's draw the axes at C. Here's my x-axis. Here's my y-axis. Sorry, my z-axis. And here's my y-axis. And I'm using the convention of all positives. I'm drawing the x-axis through C, the y-axis through C, and the z-axis through C, all the positives. Everybody good? Thumbs up?
Yeah.
Everybody good? Okay. Now, what I tend to do is I go back and I cross these guys out because I don't want to get confused. So I crossed out the z and the y-axis because when I go to look for a y or a z-axis, I want to make sure I'm looking at the right one. And I'm looking for the red ones. Using colored pencils or colored pens is really a good idea. Now what am I going to do? I'm going to draw a table.
Can you move it up a little bit?
Yes. This represents the force. This represents moment about C in the x, moment about C in the y, and moment about C in the z. And this represents the 400 Newton force, the 500 Newton force, and the 360 Newton force. What's my unit? What are my units going to be for the moment? We could do Newton millimeter or we could do Newton meter. What would you prefer? Newton meter? Okay. So remember, you always, when you do a table, and those of you who took materials got used to doing a lot of tables, always put the units up above on the column underneath the variable, and then you never have to write the units again in the boxes. Ready? Okay, put your hands out. Parallel. If one is a line and the other is a force, can the force create a spin, a moment, about the other arm?
No.
Can one force going out that way, could a force that way cause a spin around this axis?
No.
No, why?
Parallel.
Because they're parallel. If you do this, if this is the force, it can create a spin. But if a force is parallel, there can be no moment. So, if this is the x force, and this is the y force, and this is the z force, can this 400 force in the x create a moment in the x? No. Why? Because they're parallel. Can the force in the y create a moment in the y? No. Why not? They're parallel. Let me hear all of you this time. Can a force in the z create a moment in the z?
No.
No. Why?
Parallel.
Parallel. Okay, so now, remember when we do right-hand rule, The moment is equal to what? The absolute value of the force times the absolute value of the perpendicular distance. If you want to find the moment in the z and the force R cross F, and the F is in the x, what direction is the R going to be in? If the force on the system is in the x direction, and you want to find the moment about the z, what is this perpendicular distance going to be in? The y. Why is it going to be in the y direction? It has to be perpendicular. The definition of a cross product is the vector is going to be perpendicular to the two vectors in question. So if you have the x and the y, and you're crossing x and y, and you're going to get a z. So how about another one? If the moment is in the x, and the force is in the y, what is the r, the perpendicular distance in? The z. Everybody's comfortable with that? Yeah? Thumbs up? Okay, so, Chris, we're up to you. Ready? You're the first one doing 3D right-hand rule. We have a force in the x. Do you see it? Here it is,
Yep.
right here. And we're trying to find the moment in the y. What is the perpendicular distance between this 400 and this y-axis? What is the distance?
180.
Yes. Good. 180. The force is in the x. You want to put that? Let's do this. Let's say x. Let's put an x here. Let's put a z here. And let's put a y here as a remembrance. We have an x here. We want to find the moment here. This force is shooting out at you at the top of the box, right? Here you see the top of the box. And the y is on the bottom of the box. The perpendicular distance, if this is x and this is y, we need a perpendicular distance in the z, and it's the height of the box. 0.18. You said you wanted, no, are we using you know what, let's use millimeters just because that's the number and we don't have to convert. So, the moment is going to be the force, 400 times the 180. Now remember that the right-hand rule does if I multiply the magnitude of the force times the magnitude of the direction, am I getting the magnitude or am I getting the magnitude and the direction? I'm only getting the magnitude, right? So now I have to use the right-hand rule to determine whether it's positive or negative. The force is there. Put your fingers in the direction of the force. Your palm goes towards y. And are you getting a thumb in the direction of the positive y or the negative y? Positive y. We finished that one. Okay, Sarah, next one. 400. We're looking at the 400 Newton force. We're trying to find the moment about the z. So what is the perpendicular distance between that 400 force and the z? Okay, let's try again. So the 400 is in the x. We're trying to find the moment about the z, so the distance has to be in the y. I don't even see a 150.
Oh, I don't know, I was just looking at the moment that's calculated.
Okay, so here's the force. Here's the force, and the force is causing a spin about the z-axis, right? And this is in the x, and this is in the z, so we need a y distance. Let's try again. 250. It's this right here, the 250. So 400 times 250. And Janae, positive or negative? Fingers go in the direction of the 400. Palm goes towards z. Do you have your thumb in the positive or the negative direction of z? So fingers go in the force. So I'm putting my fingers on top of the box. And if you want, use a box. So look, here's our box.
The thing I don't get is the palm in the direction of the
Okay. So the fingers go in the direction of the force, right? but the Z is all the way over here. I have to put my palm in the direction of the Z and my thumb is pointing down. So would that be,
Over here?
yeah, remember it's in red.
Oh, right,
It's to the left, it's on the left side of the box.
okay.
So the force is in the middle of the box coming out at you at the top, and the Z is on the left side of the box going up. What's the positive or negative?
Negative.
Negative. Okay, Maria, next one. Now we're looking at the 500. So 500 is the Y right here. It's a 500 Newton force. I'm trying to find my moment about my x-axis. This is in the Y, this is in the x. The distance has to be in the Z. What's the distance?
180.
Correct. Positive or negative? Fingers go in the direction of the force. My palm goes towards, facing down towards the x-axis. Do you get a positive or a negative? Negative. Okay, so far, who's got it? Maybe only 10 people. Put your hands up high. Did you get it yet?
I get it, but I'm slow.
Okay, that's fine. You can totally be slow. Okay? Let's do the next one. Lonnie, 500's here. It's in the Y. We're trying to find the moment about the Z. If this is in the Y and this is the Z, the distance has got to be in the X. So it's 500 times 100. Positive or negative? Fingers go in the direction of the 500. Palm has to go towards Z, which is in the front of the box, and you get negative. Want to do that one again?
Please, the thumb is not in the direction of the Y. I'm so confused.
Okay, so let's do it on here. So we have a force shooting out. Well, I guess I can't do it backwards. The force is shooting out here. Can you see that? Can you see even the red pen? Probably not. No.
I can see it.
How about this? Okay, this is where the force is shooting out. And the Z-axis is over here, coming up. So the force, the red force, is behind the X. So my fingers go in the direction of the force, my palm goes towards the Z-axis, and it's pointing in the negative direction.
Negative in the Z.
Negative Z.
Okay.
Can it go that way?
Okay.
Say it again?
Can it go that way?
Well, you can't because if I do it that way, my fingers are going in the direction of the force, but my palm is finding a spin of something over here. You're finding the spin of the axis over here, not here. In order to find the spin that this is creating, you have to put your fingers in the direction of the force and palm goes towards Z. Another suggestion is to reduce it to 2D, because you're totally comfortable with 2D. So let's just look at the top of the box. If you look at the top of the box, put your fingers in the direction of the force, palm towards the blue, and your thumb is pointing in the opposite direction of the positive Z. So you could reduce it to a 2D. Just look at the top of the box. Fingers go in the direction of the force. Palm goes towards the Z-axis. My thumb is pointing in the opposite direction of the positive Z. It just takes a lot of practice. Not even a lot. 3 problems and you'll get it. But then when you do all the homeworks, you'll really get it. Okay, let's do the next one. 360. So 360 is here. Right, 360 going here. I'm trying to find the moment about the x-axis. The perpendicular distance has to be in the y. Lucas? So the force is in the z.
So 250.
250. 250. Positive or negative?
It's negative.
Negative. Okay. And I shouldn't have said that after 3 problems you're going to get it, right? Because if you don't get it, then you feel not so good. It's going to take a while. It takes a while to get it. And when you do all the practice with the homework, then you should be comfortable. You'll be doing it every time you do a problem, you're going to be able to do it faster and see it in 3D. Okay, next one. 360. So the force is still on the Z. DJ, we're trying to find the moment about the Y. So here we have this going down in the back of the box, and this is in the middle of the box to the right. What's the perpendicular distance?
180.
Not 180. Just take a look at this. This is in the Z. The Y is in the Y. It has to be an X distance. So it has to be either 100, 100, or 200.
200
Try again.
or 100?
100. Okay, Y. Let's take a look up here. The force is going down in the back of the box, and the Y is coming over midway in the box. So the perpendicular distance between the two is 100. Positive or negative? Fingers go in the direction of the force, Larson. Palm goes towards the line, negative. Ryan.
For our table, we just use the magnitude of the force since it's already, the
That's
direction's already
That's
specified.
correct. That's a really good question. You all remember when you do right-hand rule, you're taking the magnitude of the force and the magnitude of the perpendicular distance. What's giving you the sign is the right-hand rule. So even though this 360 is in the negative direction, I'm only putting 360 in here. I'm not putting a negative 360 because when you find the right-hand rule, it's the magnitude of the two values. When you add this all up, it's going to come out to be 180, 360, and negative 150.
You put your fingers in the direction of the force, and then your palm goes in the direction of...
That you're finding the moment about. So which one do you want to do? 360?
Yeah, it's the very last one that you
The
did.
last one. Okay.
Yeah.
So fingers go in the direction of the force.
Uh-huh.
So fingers go toward the back of the box. I'm trying to find the moment about Y, and Y is in front of the box. So my palm has to be in front. Your thumb is going in the negative Y direction.
The palm it points towards...
The axis that you're trying to find the moment about. Fingers go in the direction of the force, which means they're going in the negative Z direction. Palm is going towards the Y axis, and my thumb is running in the negative direction of Y. Okay. We're going to do this again. We're going to do another problem. Claire.
So the one that we were just talking about was
This one?
moment about C.
This one?
Yeah. So put your fingers in the force of the direction
Bottom.
on the axis at point C.
Right, and that's why I crossed off these other two, because I didn't want to confuse myself, right? So we're trying to find, the goal is to find the moment about point C. So I'm trying to find the moment about the X, Y, and Z axis through C.
So you keep saying that the y-axis is behind the point, and that's because C is in the middle of the box. So when you put your fingers in the direction of the force at point C, Y is behind it, and that's why you put your
Not
hand
Y,
down.
not Y, the point A, the force of 360 is
Oh.
behind point C. Okay?
Cool. Perfect.
So, what are the 3 ways to represent a vector? Going back to forces. One is vector form, right? What's the other way? Unit vector. We don't represent moments in unit vectors. We never use unit vectors. What's the other way?
Magnitude and angle.
Magnitude and direction angle. And is a moment a vector? Does it have a magnitude and a direction? Yes.
Yeah.
So how do I calculate the resultant? Sorry, how do I calculate the magnitude of M? Pythagorean's theorem. And what does it come out to be? 184. 184 Newton meters.
I got 237.
237?
Yeah.
Oh, I'm looking at the wrong problem. Thank you. Did somebody else get 237?
Yeah, I got 237.
Thank you. 237. So, one way to represent a vector is vector form, and yes, we use that in moments. The other way to represent a vector is unit vector, but do we use unit vectors for moments?
No.
No. Third way is magnitude and direction angle. So, theta x is equal to the inverse cosine of, we knew it before as force x over force, right? It's moment x over moment. So the cosine of -1 is 180, remember you have to put in the negatives, divided by 237, and the value comes out to be? Okay, what is it? 139.4. Does it make sense that it's obtuse? How come? Because it's a negative value. And then how do I calculate theta y? The inverse cosine of what over what? 36 over 237. And how do I calculate theta z? Negative 150 over, oh, sorry, inverse cosine, negative 150 over 237. Did you get values for that? What did you get for theta y? Chris?
98.737.
98.377, yeah, 1 decimal place. And how about theta z?
129.2.
129.2. Does it make sense that it's obtuse? Yes. And how can we check that? The inverse cosine, sorry, the cosine squared of 139.4 plus the cosine squared of 98.7 plus the cosine squared of 129.2. And does it come out to be 1? Lucas?
Yeah.
How do you get the total?
CF for versus like MCX. Yeah.
This value here?
The 180.
I just added
250
these
goes
all
in
up.
millimeters.
That's
Then
why I
she
have
like
2 lines here,
moved
so
on,
this
so
is
it's
the
really
sum.
360 times
sum,
0.25 and like
sum,
500 times 0.18.
Okay. Because these forces has 3 really forces that they're trying to find about C.
Shouldn't your units be Newton millimeters?
Well, in here, I'm going back and forth. So yes, this has got to be Newton meter. No.
She changed it.
Yeah.
The 180 is Newton meter. So let's just put, should we put decimals on these then? Do meters? See, this I think that you're going to be comfortable with. I didn't think you would get confused if I jump back and forth from newtons to, from meters to millimeters. It would just have another 3 zeros. Okay. So did somebody check it?
Yeah.
Yeah? Double checks?
Yep.
Okay. Yeah. Yeah.
If they do why I got D on
Thank you. Good job, Maria. So this couldn't have checked then.
I was about to ask that, then how did it check?
You couldn't have checked. So Nicholas probably put the right answer in. He probably put the 81.3 in.
I put 98.7, I got 0.99.
Really?
After doing all that.
I'm gonna do it too.
Okay, do it.
'Cause I believe you.
Okay, so you guys, so I have 10 minutes. Can we have a little bit of fun? And then you'll do a problem, you'll do your workshop problem with Evan, okay? So I want everybody to take a top, and I have some really cool ones. Where's that metal box?